Okay, for day 2 of chapter 10.1, we're looking at an example. You don't need to open your book. I want you to kind of not see what they have written, so we can walk through this example together. You can always walk through it again in your book. So we're going to deal with a few word problems today that are parabola word problems, basically. Okay? So look here, we have, if you've ever driven from here to Mammoth, you might have seen, oh, you can't see. There you go. They can see on the video, you can't see. Right, I said, just look at it. But have you seen all those sun things they have out in the open desert? Yeah. Troughs to capture the solar energy? Anyway, there are places like this in sunny areas like that. And more they're looking for ways to capture that kind of energy because it's so clean, you know. They don't have to burn anything to capture that energy. So this is a solar trough, which is it's a reflective parabolic surface, so it's shaped like a parabola, that is used to collect solar energy. The sun's rays reflect from the surface toward a pipe that carries water. The heated water produces steam that is used to produce electricity. So the graph of this function, they've taken this actual real world trough and shown you it in a diagram here, graphic here. And so the graph of it has this equation. So they just hand you the quadratic equation. So you can see it's a pretty basic one, right? We have y equals ax squared. We don't have plus anything, so I guess it would be plus 0. So it just has a vertex right at 0, 0 here. So this is the part of the parabola we're looking at, which is a little darker black. So it models the reflective surface, the reflective part of this trough, where x and y are measured in meters. So each of these units that you see here are measured in meters. Use the graph to find the domain and range of the function. So these are a lot of tough words, but really you know what domain is, right? Which letter is represented by domain? X. So we're talking about what are the x values of this trough. So when we look at it, can you tell me the extreme? We just want to identify what are the smallest and the largest x values. When you're asked to find the range, if possible, find the smallest and the largest. Sometimes we have an infinite side, right? But when we look at this, we're looking at the x values, right? So as we look at this trough, do you see that the trough goes anywhere from here to here, right? So what are those units there? 1, 2, 3, 4. It looks like 5. It's hard to see. There's a blue line here. But it looks like it's crossing at 5 and probably 1, 2, 3, 4, 5. Right there. So x can be, what's the greatest thing x can be? 5. And the least thing? I could say negative 5. So x could be greater than, could it be equal to? Yes. Yes? And it can be greater than or equal to. So those are the extreme x values for this trough. Now that we know that, we can try to find the extreme range, you know, the y values. And do you see where they would be? They're kind of in between, aren't they? I mean, they're not exactly at the intersection of two of these blue lines. So how else could we find the range, the y's? No, because we're just looking at, I don't think this is perfectly calibrated, we're just looking at this, the surface of the trough, from here to here. And see, these locations, there, that's the highest, right? And here, that's the highest. They're the same, aren't they? Right? And then the lowest is here, right? And so given this coordinate plane that's laying on top of the trough, right here, the lowest part would be considered what? 0? Okay? So this trough can be greater than or equal to 0, but how high does it get? What way can we find that? Plug it in. Right, here's our equation. So what's the x value? What's the x value at this extreme point here? 5. Or the other one would be negative 5, and they're both going to give us the same value when we square it, right? So we would say y equals 0.09 times 5 or negative 5 squared. So it's 0.09 times 25. And does anybody know what that is? 25 25.09. 5 times 9?
45.
18 plus 4?
42.
How many decimal places? There it is, 2.25. And they said what were the units here?
Meters.
Meters. So there you go. It can be as high as 2.25 meters. And we found that by using the domain, right? The domain was easy to see, and we plugged it in the given equation, and there you have the highest this trough is. So this is pretty big if you think about the meter stick. Here's a meter stick. This is a meter stick as well. I've got two. Let me pause that. I'm sure it's built to take the weather. Okay, so if in that same example the reflective surface extended just 4 meters on either side, can you please find the domain and range of the function? Okay, Michael, what's the domain then? You have to say, with respect to x.
Okay. X equals 1, x equals 4.
Well, no. The domain is, give me all the possible x values. Michael.
It's x is greater than -4 and less than 4.
Okay, or could it be equal to?
Yeah, equal to.
Okay, so make sure you have that. So there's your domain. It could go anywhere from that to that. So totally 8 meters across if you were to see the entire span. And the y, the range.
I'm still working on that.
We were given this equation, right, to find the value. If we plug in, 0.09. Okay, so we're saying plug in 4 and multiply by 0.09. And Michael says that 0.09 times 16 is, what did he say? Is that right? Got what? Well, we can do it really quick. 54, 5, 14, 1.44. So you're really close. Good
Oh,
job.
yeah.
So 1.44 is the greatest height, and the least height, everyone? 0 again at the center. So it could be anywhere from 0 to 1 point. Okay, so quietly, how does the graph of y equals x squared plus 2 change if we have y equals x squared minus 2? Jot your notes down. How does that change? Give me as much detail as you can. Okay, so try to give me as much detail as possible in as few words as possible. Who thinks you have it in as few words as possible? Lauren?
Well, from that y equals x squared plus 2 is a translation of 4.
Excellent. She says it's a translation -4. So we went from being at 2 to being at -2, so we had to travel down 4. So this would be the fastest way to describe this transformation. Okay? Okay, so you're not going to graph, look at page 632. Look at it. I want you to be able to look at that and say what the transformation is by examining the math part. I think you've done enough of the graphing. We did more graphing today. So now, see which, the connection. That if you want to come up here and use the graphing online calculator to see, you may. Okay?